So let's do a problem example right now and see how we can apply some of this stuff. So let's say we have a 2 microcoulomb charge which is held stationary, and that is in our problem we're going to make this Q2 right over here is our 2 microcoulomb charge, that one. And the question is, how much work is required for you, i.e. an external force, to bring a 10 microcoulomb charge from 4 meters away, so Q1 is our 10 microcoulomb, from 4 meters away right there, to move it to right there. And we're assuming that it's going to start at rest and end at rest. How much work is required by you to do that? So our Q1 is right here is 10 microcoulombs, Q2 is 2 microcoulombs, and that is the stationary charge. So as you may guess, to figure how much work is required, we're going to need to use conservation of energy. So we start off with E initial plus work non-conservative equals E final. Now for its E initial, which charge are we going to say is causing the electric potential and which charge is being affected by it? We're moving Q1. That means Q2 has got to be causing the electric potential. So E initial, so Q1 is going to be Q1 times the V caused by Q2 will be our initial potential energy. So I'm going to draw this. U initial is the only energy it has. We're assuming it at its rest. Same thing. And when we're done, it's at rest too. So U final, again, only potential energy will be left. And U initial is just Q1 times V initial. This V that it has right there is caused by Q2. So we'll see that come in a minute here. The work is, the non-conservative work is the work that we're going to do. And then the final energy it will have will be Q1, the one we're moving, times the potential caused by Q2. So you'll see where that comes in right here. It's Q1 times the potential caused by Q2 is KQ2 over R initial, which happens to be 4 meters. Again, this is the work that we're doing, and this is the final potential energy of Q1, which is Q1 times the potential caused by Q2. And we can get rid of that one now. As we continue with this derivation, we have the work non-conservative, we're just solving for that, is KQ1, Q2 over R final. That's this term. And you subtract this term right here, KQ1, Q2 over R initial. And then when we plug in the unknowns here, what we get is this. The work that we do is 0.045 joules and it's positive. Let's make sure that makes sense. Here's a positive charge. Would it take us positive or negative work to bring it in closer to another positive charge? It would take us positive work.